Welcome to our comprehensive guide on comparators in digital electronics. In this video, we'll explore what comparators are, why they're essential, and how they fit into the broader world of digital circuits. Comparators are fundamental components that help us determine the relationship between two binary values. Whether you're a student, hobbyist, or professional, understanding comparators will deepen your knowledge of digital systems. Let's start by defining what a comparator is and why it matters in digital design. Comparator is a digital circuit that compares two binary numbers and outputs a result based on their relationship. The output typically indicates whether one number is greater than, less than, or equal to the other. Comparators are widely used in digital systems for decision-making processes, such as sorting, arithmetic operations, and control applications. By providing a simple yes or no answer, comparators help digital devices make logical choices quickly and efficiently. Let's look at how a basic comparator operates. When two binary inputs are fed into the comparator, it checks each corresponding bit, starting from the most significant bit. If the first bit is different, the comparator can immediately determine which number is larger. If the bits are the same, it moves to the next bit, continuing until a difference is found or all bits are checked. This process allows the comparator to quickly output whether one input is greater, less, or equal to the other. One-bit comparator is the simplest form of comparator. It compares two single-bit binary values, A and B. The output consists of three signals, a greater than B, a less than B, and a equal to B. This basic building block is often used in larger comparators to compare multi-bit numbers. Understanding the one-bit comparator is crucial, as it forms the foundation for more complex comparison circuits. Understand how a one-bit comparator works. Let's examine its truth table. The table lists all possible combinations of inputs A and B and the corresponding outputs. For example, if A is 1 and B is 0, the output indicates that it is greater than B. If both are 1 or both are 0, the output shows they are equal. This logical structure makes it easy to see how the comparator determines relationships between inputs. Comparators are built using basic logic gates such as AND, OR, and NOT. For a one-bit comparator, these gates are arranged to produce the correct output signals based on the input values. The combination of gates ensures that the comparator can accurately detect when one input is greater, less, or equal to the other. This gate-level design is the foundation for all digital comparison operations. Two-bit comparator extends the concept by comparing two binary numbers, each with 2 bits. The circuit checks the most significant bit first, then the least significant bit if needed. The output still consists of 3 signals, greater than, less than, or equal. This type of comparator is commonly used in digital systems that require comparison of small numbers, such as counters and registers. Designing a 2-bit comparator involves connecting multiple logic gates to handle all possible input combinations. The circuit must account for cases where the most significant bits are equal, requiring a check of the least significant bits. By carefully arranging the gates, the comparator can output the correct result for any pair of 2-bit numbers. This design process is a great exercise in digital logic. For larger numbers, multi-bit comparators are used. These circuits compare binary numbers with more than 2 bits, such as 4-bit, 8-bit, or even 16-bit values. Multi-bit comparators are essential in processors, memory modules, and digital controllers. They operate by cascading smaller comparators or using more complex gate arrangements to handle the increased number of bits efficiently. Cascading is a technique used to build larger comparators from smaller ones. For example, two 4-bit comparators can be connected to create an 8-bit comparator. This approach allows designers to scale up comparison circuits without redesigning from scratch. Cascading is widely used in digital systems where flexibility and modularity are important. Magnitude comparator is a specific type of comparator that determines the relative size of two binary numbers. It outputs signals indicating whether one number is greater, less, or equal to the other. Magnitude comparators are commonly used in sorting algorithms, arithmetic units, and digital control systems. Their ability to quickly compare values makes them vital in high-speed digital applications. Comparators play a crucial role in many digital systems. They are used in arithmetic logic units, ALUs, memory address decoding, data sorting, and signal processing. Whenever a system needs to make a decision based on the relationship between two values, comparators are involved. Their speed and reliability make them indispensable in modern electronics. Integrated circuits, ICs containing comparators, are widely available. These ICs simplify the design process by providing ready-made comparator functions in a compact package. Common examples include the 7485 and 74LS85 series, which offer 4-bit magnitude comparison. Using comparator ICs saves time and ensures consistent performance in digital projects. Comparator ICs come with specific pin configurations. Each pin has a designated function, such as input, output, or power supply. Understanding the pinout is essential for integrating the IC into your circuit. Datasheets provide detailed diagrams and descriptions to help you connect the comparator correctly and avoid common mistakes. Speed at which a comparator operates is important in high-performance digital systems. Fast comparators can make decisions in nanoseconds, enabling rapid data processing. Timing characteristics such as propagation delay are specified in datasheets. Choosing the right comparator for your application ensures optimal system performance. Power consumption is another key factor when selecting a comparator. Low-power comparators are ideal for battery-operated devices and portable electronics. Datasheets list the typical current draw, helping designers balance speed and efficiency. Efficient comparators extend battery life and reduce heat generation in electronic systems. Comparators can have different output types, such as open collector, push-pull, or tri-state. The output type affects how the comparator interfaces with other components in the circuit. For example, open collector outputs allow multiple comparators to share a common line, while push-pull outputs provide faster switching. Understanding output types helps you design robust digital systems. Noise immunity is the ability of a comparator to resist unwanted electrical disturbances. High noise immunity ensures reliable operation, especially in environments with electrical interference. Designers use filtering techniques and proper grounding to enhance noise immunity. Selecting comparators with good noise performance is vital for stable digital systems. Hysteresis is a feature that helps prevent false triggering in comparators due to small input fluctuations. By introducing a small difference between the switching thresholds, hysteresis ensures stable output even when the input signal is noisy. This is especially useful in applications where precise and reliable comparison is required. It's important to distinguish between comparators and subtractors. While both circuits deal with two inputs, a subtractor outputs the arithmetic difference, whereas a comparator only indicates the relationship between the inputs. Comparators are faster and simpler for decision-making tasks, while subtractors are used for calculations. Many modern microcontrollers include built-in comparators. These on-chip comparators allow for fast, efficient decision-making without the need for external components. They are commonly used in analog-to-digital conversion, threshold detection, and signal monitoring. Integrating comparators into microcontrollers streamlines circuit design and saves space. While our focus is on digital comparators, it's worth noting that analog comparators also exist. Analog comparators compare two voltage levels and output a digital signal. They are widely used in analog-to-digital converters, oscillators, and voltage monitoring circuits. The principles are similar, but the applications can differ. In signal processing, comparators are used to detect specific signal conditions, such as zero crossings or threshold levels. This allows systems to respond to changes in input signals quickly and accurately. Comparators are essential in applications like waveform shaping, pulse generation, and digital communication. Sorting circuits often rely on comparators to arrange data in a specific order. By comparing pairs of values, the circuit can determine which should come first. This process is fundamental in digital systems that require data organization, such as memory management and database operations. Arithmetic logic units, ALUs, use comparators to perform operations like maximum, minimum, and equality checks. By integrating comparators, ALUs can quickly determine the relationship between operands, enabling efficient computation. This is especially important in processors and digital controllers. Comparators are used in memory addressing to match requested addresses with stored locations. When a match is found, the comparator signals the system to access the correct memory cell. This process is vital for fast and accurate data retrieval in computers and embedded systems. In control systems, comparators help make decisions based on sensor inputs or feedback signals. For example, a comparator can trigger an alarm if a temperature exceeds a set threshold. This decision-making capability is crucial for automation, safety, and process control applications. Digital communication systems use comparators to detect signal levels and synchronize data transmission. By comparing incoming signals to reference levels, the system can accurately interpret data. Comparators are essential for error detection and reliable communication in networks. Timers and counters often use comparators to determine when a preset value has been reached. When the comparator detects a match, it can trigger an event, such as stopping a timer or incrementing a counter. This functionality is widely used in digital clocks, event counters, and automation systems. Security systems use comparators to monitor inputs and detect unauthorized access or abnormal conditions. For example, a comparator can check if a code matches a stored value, granting or denying access. This quick comparison is vital for maintaining safety and security in digital environments. In robotics, comparators help robots make decisions based on sensor data. For instance, a robot might use a comparator to determine if an object is within a certain distance, triggering a response. This enables robots to interact intelligently with their environment and perform tasks autonomously. Industrial automation systems rely on comparators for process control and monitoring. Comparators can compare sensor readings to set points, ensuring that machinery operates within safe limits. This real-time comparison helps maintain efficiency, safety, and product quality in manufacturing environments. Automotive electronics use comparators for functions like engine control, safety monitoring, and diagnostics. For example, a comparator can check if a sensor reading is within the expected range, helping to detect faults early. This contributes to vehicle reliability and performance. Consumer electronics such as smartphones and home appliances use comparators for various control and monitoring tasks. For instance, a comparator might help regulate battery charging or manage power consumption. Their versatility and reliability make comparators a staple in everyday devices. Medical devices use comparators to monitor vital signs and trigger alarms when readings exceed safe limits. For example, a heart rate monitor may use a comparator to detect abnormal pulse rates. This ensures timely intervention and enhances patient safety in healthcare settings. Test and measurement equipment often use comparators to evaluate signal levels and verify circuit performance. By comparing measured values to reference standards, the equipment can quickly identify faults or deviations. This is essential for quality control and troubleshooting in electronics manufacturing. Educational kits for learning electronics often include comparators as key components. These kits help students understand digital logic and circuit design by building and experimenting with comparators. Hands-on experience with comparators lays a strong foundation for further study in electronics. In research and development, comparators are used to prototype and test new digital systems. Their simplicity and versatility make them ideal for rapid experimentation. By using comparators, engineers can quickly evaluate design concepts and optimize circuit performance before moving to production. When designing with comparators, engineers must consider factors like speed, power, noise immunity, and output type. Balancing these parameters ensures the comparator meets the needs of the application. Careful design leads to reliable, efficient, and high-performance digital systems. Some common problems with comparators include false triggering, noise sensitivity, and incorrect wiring. These issues can lead to unreliable operation or circuit failure. By understanding potential pitfalls and following best practices, designers can avoid these problems and create robust comparator circuits. Troubleshooting comparator circuits involves checking connections, verifying input signals, and measuring outputs. Using tools like oscilloscopes and logic analyzers can help identify faults. Systematic troubleshooting ensures that the comparator operates as intended and helps maintain circuit reliability. Before building physical circuits, designers often simulate comparator circuits using software tools. Simulation allows for testing different configurations and identifying issues early. This approach saves time and resources, leading to more efficient circuit development. As digital technology advances, comparators are becoming faster, smaller, and more energy efficient. Emerging applications in artificial intelligence, IoT, and high-speed computing demand even better performance. Ongoing research continues to push the boundaries of comparator design and application. Let's recap what we've learned about comparators in digital electronics. We covered the basic operation, different types, applications, design considerations, and troubleshooting tips. Comparators are essential for decision-making in digital systems, and their versatility makes them invaluable in countless applications. Thank you for joining us on this journey through comparators in digital electronics. Whether you're designing circuits, learning about digital logic, or exploring new technologies, understanding comparators will serve you well. Stay curious and keep exploring the fascinating world of digital electronics.